But just before we move on to introducing that speaker, we do have a number of sponsors who've made this event possible. And so I want to give a shout out to JetStack and just quickly introduce what JetStack do. So JetStack is a cloud native technology and services provider. They've been active since the very beginning of Kubernetes, and they were one of the original members of the CNCF. JetStack has become particularly well known for its work in open source development and is the original creator of the Cert Manager project, which has grown in popularity as a fully open source solution. As a cloud-native ecosystem has grown, JetStack has evolved as a professional services company and has deep experience helping enterprises building platform infrastructure using Kubernetes. In recent months, JetStack has launched security-focused products to give both enterprise platform and security teams full visibility and control of their machine identities to protect workloads and ensure cluster health across any type of cloud-native infrastructure. As an open source company, their culture and values are centered around community. They're also growing really fast. So they're looking to talk to any talented engineers out there. If you're interested, please check out their website to see what opportunities exist. And so we are ready for our final speaker for track 2. He probably needs no introduction. We've seen him a bit over the last couple of days, but I am very, very pleased to introduce one of my co-organizers, Mr. Matt Jarvis.
Thank you, Paula. Right. Well, I'm going to attempt the magic trick of doing a 35-minute presentation in 25 minutes. So don't try this at home, folks.
You've got this, Matt. You got it.
Right. Let's just, I need this. And, are you seeing my screen there?
Yep, indeedy.
Okay, cool. Right, let's get going. So, this is me, Matt Jarvis. I'm sure you're bored of me by now after being on screen so much in the last 2 days, but I'm a Director of Developer Relations at Sneak. And today we are going to be talking about how most exploits are a combination of application level vulnerability together with infrastructure misconfiguration, which allows an attacker to extend the blast radius of the initial attack into your network via a vulnerable app. And I'm going to walk you through what this could look like in a Kubernetes environment. So our starting point for today's demo is that we have discovered this vulnerable web application on the internet, and this is a remote command execution vulnerability. It's clearly mocked up for the sake of this demo, but there are lots of real-world examples of this. There's one almost exactly like this for Tomcat, and so these do actually exist. At this point, all we know is that we have found an application with this vulnerable app on port 80, which we've connected to. So let's also introduce our timeline of doom. And the timeline of doom is going to track how our exploit scope, how wide our blast radius is, has extended over time. So let's have a think about what we might be able to do from here. So the first thing we might be thinking about is that most applications now run in containers, and most containers are configured with environment variables. So looking at the environment variables of our application might tell us some interesting things. And so if we do command equals env, that does indeed give us lots of interesting information. So we've got multiple references to Kubernetes, so we can clearly ascertain that we're running in a Kubernetes cluster. We can also see the internal address of the API server, and we can also see that whilst we're exposed on port 80, we're clearly running a service on port 5000 internally to the cluster. Typically, that's obviously how pods get exposed to the external world. So we can now update our diagram of what we know. So we've discovered the Kubernetes cluster. We know there's an internal IP address to the API server, and we know that we've got a service there. So let's see what else we can find out. So what we might be interested in is the networking information. So let's run the IP command there. And we've discovered the IP address of the pod, and this is going to be useful to us later. So we're going to make a note of that 10.244.1.9, and we'll come back to that a little bit later, and we'll see why that's important. So let's see what else we can do. By default, every pod in Kubernetes has a service token auto-mounted in it. This is associated with the service account that was used to create the pod. You can control whether this is auto-mounted on a service account or a pod level using auto-mount service. Account token is false, but let's see whether we can find that in our pod. So I'm just going to have a cheat slightly here because this is a bit of a longer convoluted command. So I want this one. So let's just copy that and let's run that. So what I've done here is to cat where I think the token might be, and clearly I do have a token auto-mounted here. So it seems that our permissions for this particular pod will let us access the token. So if we go back to our timeline of doom, the next thing that we can add to our exploit scope is that we've discovered a pod token. We have some credentials, and every attacker, the aim of every attacker is to gain credentials to expand their exploit. So let's see whether we can use that token to get some stuff from the internal address of the API. So again, we're going to construct a URL here to run this remote command. And what we're going to do is test whether we've got curl. We clearly have, because we're getting information returned from the API server here. And what we've done is see if we can access this endpoints API of the API server. And this has actually returned us a bunch of data. Now, this Kubernetes cluster is actually running on my laptop, so I know where the API server's external IP address is. But in many real-world clusters, this will give you the IP address and the port of the external address of the API server. And so, if we go back to our diagram here, what we've done is go from our pod to the internal IP address of the API server, and we've passed it the token, and it's given us back the external IP address of the API server. And we can now add another vulnerability in here that pod token has allowed us access to the endpoints API. So it's a too permissive policy on the service token that's allowed us to discover additional information about the Kubernetes cluster. So now we've got a token. Let's see if we can configure our local kubectl to use this token, which will make it a bit easier for us to continue our attack. So I've got a little script here to set up my my kubeconfig, and I'm just going to add that token that we've just found, and my address of the Kubernetes API server is going to be that. So let's just pull this out a bit so we can see what we're doing here. So let's make sure that we've kubeconfig equals /demo kubeconfig. Right, so the first thing that we've got, what we might want to be interested in, is to see what pods are running. So let's just do kubectl get pods in the default namespace. And what's interesting here is that we've immediately had an error that we're not allowed to run to get pods in the default namespace. But so that's the service token is not permitted to, hasn't got the permission to get hold of the pods objects. But it has given us some more information here, because what we can see here is that we can see the service account that was used that token is related to. And we can see the service account is namespaced into this secure namespace. So let's try and get pods in that namespace, and we can see that command has actually succeeded. So clearly this token in this secure namespace has some permissions. So let's look what permissions it actually has. And there's a couple of different ways we can go about this in Kubernetes. We can use the kubectl auth command. Can I --list --token equals, and then our token. And this is in the default namespace. I didn't namespace that command. So we can see we don't have actually many permissions here. We've got that endpoints permission there. But other than that, we don't have very much. But if we now repeat that for our secure namespace, we can see that we've got a whole bunch of permissions here against all resources in this namespace. And there's also a different way we can visualize this. What we can do is use the Access Matrix plugin, which gives us a different view. This is a crew plugin that I've got installed. So if we do that in the secure namespace, we can see we've got all sorts of permissions on all sorts of things. So this is a fairly common kind of misconfiguration here. It's a fairly common pattern where people assume that namespaces are actually a security boundary. So I've got a service account, it only exists in this namespace. I can let it do what it wants in that namespace, providing I don't allow it to do anything else in other namespaces. So now we go back to our slides. We know we've got our external IP address of the API server that I connected to. We know we have a default namespace. We don't know what's in it. We know we've got this secure namespace. And the vulnerability here is that role has been given too many permissions. So it's a service account that's been given too many permissions in that namespace. As I said, it's the idea being that somehow a namespace is a security boundary. So again, we'll update our timeline of doom. So we've got this role with too many permissions in the namespace. So let's try and get a shell on our compromised pod. So if we do kget pods in our secure namespace, we've only got one there, so we can assume that is the one that we compromised externally. So now I could do kexec -it. I've just got kubectl alias to be k there, if anybody's wondering. So we need that pod in the secure namespace. And let's try and run bash. And so this gives us a shell. So that's interesting. So I can see that I'm not the root user, which is good. So I'm running as this web admin user. So the first thing that I'm going to try and do is become root. So I'm going to do sudo su. And the sudo command doesn't even exist in this container. So this is good from a security practice perspective. You know, we're running as an unprivileged user. We're not allowing sudo. So let me try something else. I'm going to try and create a file. And so that has worked. So I've been able to create a file there, which is another vulnerability here. If we've got a read-write file system that allows attackers to download software, potentially change configuration. I know I have curl there already, so it's definitely possible I can now download tools from other places. And this is caused by not setting read-only root file system is true in the security context settings for my container. And you know, there are, in most scenarios, you really don't want to have read-write file systems inside containers. You know, we're not storing stuff in there, and it only gives an attacker an additional way of exploiting your containers. So I'm going to come out of that for a second. And so we know we have permissions in this secure namespace. So let's try and spawn a root pod. And I've got some YAMLs here. And if I look at the root pod YAML, so this is just going to spawn a Alpine container, which I know runs as root. So let's try and actually run that and see what happens. Root pod. In the secure namespace. That I've got that error there because I tried to do it in default. Well, that looks like something's happened there. So let's have a look what's actually happened there. So we've got this create container config error. So that looked like something has actually stopped us from running the root pod. And if we do kubectl describe the pod, root pod in the secure namespace, and this error here, container has run as non-root and image will run as root. So something there has stopped us from running a root container. This is probably a pod security policy, but at this point we don't really know. So let's try and run a privileged pod and see what happens. So demo YAMLs, I'm going to run non-root, but I'm going to try and spawn a privileged pod. So I've got this container image of mine that's in a public registry, and I'm going to spawn it privileged, but it's running as a normal user. And I'm also going to try and do a host path mount. So I'm going to try and mount the host file system in this container. So if I apply this one, let's see what happens. Non-root, privileged. in the secure namespace. And now we can tell that we definitely have a pod security policy, because we're getting an error saying the pod security policy will not let us admit that pod because privileged containers are not allowed. So there's a pod security policy in place on this secure namespace. So that's kind of interesting. You know, that's a good thing right from a security perspective. So let's try and do something else. So now I'm going to try and run non-root, non-privileged container. And again, I'm going to use my super sneaky container image that's running in that's from a public registry, but I'm not going to run privileged. I'm going to run as a normal user. So let's just apply that. Demo YAMLs, non-root, non-prov in the secure namespace, and something seems to be happening there. So let's have a look what's happening. So my sneaky pod is up and running. So again, this is another vulnerability here, because what's happened is this cluster has let me pull arbitrary container images from public registries. And I built this container image, so I've been able to pack it full of all sorts of hacking tools that I need in order to extend my exploit. So I know that in my sneaky container, I've got a service running. So what I'm going to do is do a port forward to my new container that I've just launched on port 8080. And now what I'm going to do is I'm going to open another tab here, and I'm going to do localhost, and I'm going to, let me just bear with me 1 second. What I'm going to do is to connect to that port 80. That's what I need. Let's just copy that. Okay, now I'm going to connect to localhost port 8080, and I'm running a remote TTY on this container image, so on this pod. So I've been able to have another access into the cluster here. And, you know, when I do who am I in this pod, I'm the sneaky user. So clearly I'm not root, but what I can do is that, and I've been able to achieve root by running sudo. And the problem here is that the pod security policy doesn't include allow privilege escalation equals false. So we've this setting here, allow privilege escalation equals false. And many people think that that is redundant if you have set that you don't allow privilege pods and you don't allow running as root, but it's not redundant, and I'll show you why. Let's come out of the root user again. And so what I'm going to do is to try and map the network here. So I'm going to do use nmap, which I had in my sneaky pod, minus pn minus n. Let's open 10.244.1. Oh, I need the. So let's just see what IP address we are. 14, right? So. 244.1.14/24. So as a normal user, I have not been permitted to run that nmap command because nmap requires kernel level privileges, capabilities, which a normal user doesn't have. But if I sudo su there, and I run that same command, now I'm able to run the network. And this has told me a couple of things. Firstly, it's told me that there is no network restrictions in place to stop me from going out of a pod and randomly scanning to other things. And secondly, it has told me that I know about this particular application, 10.244.1.9, you'll remember, was the IP address of our original vulnerable application that was running on port 5000. But what the scan has shown us is another application also running on port 5000. Now that's very interesting to me. That could well be another instance of my vulnerable application. So before we go any further with looking at that, let's add our pod security policy didn't disallow privilege escalation. That allowed me to sudo. And we can add some more information. We've discovered another pod running on port 5000. We don't know anything about it at the minute. We don't know which namespace that new application's in. But we can also add to our timeline of doom that we have no network controls in place. So we had nothing, no policies, no service mesh that stopped us from connecting from one pod into another pod, potentially escaping our namespace. So what we're going to do now is from my sneaky pod, I'm going to now try to create a tunnel to this new pod. And so I'm just going to grab my SOCAT string here. So what I'm going to do is to create a tunnel. So I'm going to use SOCAT, and I'm going to go to 10.244.1.10 port 5000. I'm going to represent that in port 5001 on this pod here. So I'm going to create that tunnel, and now I'm going to exit out of the port forward that I already had there on the original on my sneaky pod, and I'm now going to reconnect to that port 5001. And so that's now connected. So now if I now create another, I want to go localhost on port 5001. And lo and behold, it is another example of our vulnerable web application. So when we do, let's see whether we can see whether this one has a token in it. Just bear with me. It's not very helpful. Let's just copy that. And now I have another token. So let's just take that token and let's see what we can do with this new token that we've got. So let's just, if I just manually change over to this new token in my kubeconfig. So one token, go on, new token, and let's just comment that one out. And let's try kubectl get pods. So I'm now able with this new token to find out what pods are running in the default namespace. So let's have a look run the kauth cani command, what this new token has given us. And we can see we've now got lots of permissions in the default namespace that we didn't have before. So we've been able to escape that secure namespace, and we've got new permissions in the default namespace. So again, we created that tunnel from 5000 to 5001, and we know now that this pod is running in the default namespace. So let's try and do something else here. So if we now look at our, we're going to try and run a privileged pod here. As I said, it's going to run that same container image. It's going to try and mount the host path, do a host path mount of the root file system of the host. So if we now apply that, YAMLs non-root privileged pods. So we can now see that we've been able to start a privileged pod in this default namespace. So let's just get onto that that particular pod. Kexec IT non-root dash. And what we're able to do now is to, we know we can run sudo here, so I can become root. And if I run the ps command here, I'm still only seeing the things, the processes that are running inside the container, even though I'm root. But I had the host file system mounted in that, that /chroot folder. So what I can now do is use the chroot command to change my route to the root of the host of the node. And so now when I run the PS command, what I'm actually seeing there is all the processes that are running on the node itself. So I've basically been able to compromise the underlying node. We can see the container D processes. We could see some of the control plane is running here. We could potentially see other container images that were running on the node. And if we update our scenario, like we've been able to create that privileged pod, so there was no pod security policy in default. We've been able to mount stuff on the host. And again, our timeline of doom, there was no restrictions in the default namespace. So once I've got the hosts file system here, we can do all sorts of things. So the first thing that I'm going to do is to get the kubelet token. So I'm going to set export kubeconfig to etc. Kubernetes kubelet.conf. And I'm going to see whether I have kubectl on the node, which I do, and kubectl in the kube. I'm going to look what pods there are in the kube system namespace. And so these are all the pods that are running the Kubernetes cluster itself. So this is all the control plane, all the things that are running the cluster. And I'm able to get all sorts of information about those pods, which nodes they're running on, which is going to be very interesting to us in a second. And I can also get the names of the nodes. So none of our other tokens let us do this. This is the token that the kubelet is using on the node to spawn pods. Now, what's interesting about the kubelet token is that I can't actually spawn very easily if I do tty minus minus. I'm going to try and spawn a busybox pod here. Image equals busybox minus minus restart equals never. I'm going to run a shell. And I actually get forbidden there because the kubelet token isn't actually allowed to start pods like that. But it does say it can create mirror pods. And this is another way I could attack this node. In the etc. Kubernetes manifest directory on a node, if we put YAML in there, that will get automatically started. So we could start to create pods in the kube system namespace. We could make other attacks against the kube system, against the cluster itself by using mirror pods. But because we've escaped the pod security policy and we now know which nodes we have, we can actually attack on a different vector at this point. So we're going to launch a pod to the node hosting the etcd cluster. And in the pod configuration, we're going to actually mount the etcd configuration from the node so that we should be able to connect to etcd using the node credentials. So if we have a look at our demo YAMLs etcd client, we can see what we're going to do here is mount the host file system, mount where the etcd cluster configuration is, and then we're going to basically pass in all of our configuration for etcd, and that will let us connect to the etcd cluster that's running inside our Kubernetes cluster. So we're going to apply that. Right, and our etcd client is now up and running. So what we can do is we want to exec our etcd client, and we're going to run etcd control member list. And this is just to check whether we can connect to etcd, and we can see we can because we've returned the members of our etcd cluster. And etcd contains a lot of interesting information about the cluster, not least of which is a bunch of secrets. So let's see whether there's any secrets in this particular etcd cluster. And I'm going to slightly cheat here with my string. Let's just get that and run that. So we're going to query etcd and we can see we've got lots of secrets here. And the one we're particularly interested in is this one, because we know that this token has cluster admin rights. So if we now, let me just get the string here, to get that, and we want those CM779. Clients. Bear with me 1 second. control. Yes. Group system. Application controller. Token. And the string on the end was DXF9F. That was my mistake. DXF9F. Right, and now we have a token for that particular role. So now when we take this token and we do kubectl auth can I minus list minus token equals token. And what we can now see is that this token has all of these permissions on the cluster roles. So I can update roles. I can basically do anything I want to any user account that's on the cluster. So that's really the end of the, so just to go back over what we just did, we created, we know that the etcd cluster is running on a particular host. We started an etcd client pod to connect to that etcd cluster. And finally, we got cluster admin rights. We found a token in etcd that has the ability to change cluster roles. So at that point, it is game over. I now pretty much own this cluster. I can do whatever I like. So how could we have prevented this? Well, firstly, we could have avoided having a vulnerable application right at the start. So scanning your application code for upstream vulnerabilities is extremely important before you get to production. We could have been scanning our Kubernetes YAML files before we deployed things. So most scanners, Sneak included, will tell you about many of the things, the misconfigurations that I just talked about in this talk. And finally, scanning our container images. So making sure that our container images don't have vulnerable applications in them. You can sign up for a free account and try all that out with Sneak at app.sneak.io. I would like to give lots of props to Mark Manning in Coldwater and Duffy Cooley, who actually did a lot of the work that this presentation was based on, and to many others in the awesome Kubernetes security community. So with that, I am done. Let's just, there we go. Hello, Josh. You're not Paula.
No, I'm not. How's it going?
Good.
Fantastic talk, Matt. I don't think we have any questions to check in the YouTube. No. And Slack? No questions.
Awesome. Well, in that case, we should head back over into track one.
We should.
Do the ending of the day and of the conference. So thank you, everybody, for watching track two today. I hope you've enjoyed all the talks. And we'll see you back over in track one.
For those who are watching, I'll post a link in the YouTube chat to track one, where we'll be doing a wrap up. Thanks very much.